stands for Gaussian free field, and quantum gravity, quantum so far in brackets, so in quotes, there will be gravity. So right. So many people at your seminar are interested in Liouville quantum gravity, and when Polyakov came up with this model back in 1981, he wrote in the paper. It starts with an idea that we need a novel tool set to study physics phenomena, and this tool set is a summation over surfaces to replace, to generalize the summation over paths in Feynman's quantum mechanics. And initially, he was looking for physics applications. What he had in mind was a string theory description of quantum chromodynamics. In particular, the strings which arise as interaction of quarks. But that didn't quite pan out as was hoped. But instead, Liouville theory gave rise to many interesting phenomena. Apart from mathematics, there was a 2D conformal field theory. More recently, there are new connections to kind of quantum chromodynamics, which is supersymmetric Young-Mills theories. However, it would be nice to relate such a nice in the physics theory to observable phenomena. And there were many ideas, apart from what I briefly mentioned here, what kind of phenomena this could be. And I'm going to talk about one kind of interesting candidate where this this Liouville quantum gravity can be relevant. And this is the quantum Hall effect. So this is so far speculative, right? So this is in the end, I'm not going to construct a quantum gravity theory of quantum Hall effect. But there are some interesting parallels. So I have to say that this is based on conversations and collaborations with Paul Wigman and Steve Zeldich and others, but I not always mention the names properly. And please ask questions. Please interrupt. And I don't have so many slides, so if you pose the questions, that would be excellent. So first, I give you a brief crash course into quantum Hall effect. I imagine not everybody heard about this. So this is a real experiment, and it to understand it, look at the picture here, this one. So it happens in 2 dimensions. So this is a 2-dimensional material here. It's kind of sandwiched between 3-dimensional materials. One of them is conductor, one is insulator. And electrons live at the 2-dimensional interface here. So, and these electrons here, they are placed in perpendicular magnetic field. Magnetic field B is perpendicular to the plane at all points. And what happens is that if you try to make current in direction X, Ix is a current, due to magnetic field, electrons turn sideways. So magnetic field makes them not go straight. And you measure actually the voltage across the device, voltage in direction Y, perpendicular, in direction Y. And the coefficient between current and voltage is called resistance. And this resistance is Rxy. So when you take the voltage Y divided by current Rx, you get this Rxy. So in classical physics, should be a straight line as a function of magnetic field. So you make magnetic field stronger. In classical physics, you observe straight line on this graph. In quantum physics, meaning certain material taken, it's called gallium arsenide, taken at very low temperatures, instead of straight line, you observe kind of monotonic function which passes through plateaus. At some point, there are these plateaus. And these plateaus are very straight. And on the plateaus, the value of this Rxy is a rational number of the type P divided by Q, where meaning P and Q are small numbers, like 2/3, 1/3, 5/7, etc. So kind of rational numbers with small p and q. So for example, this plateau corresponds to the value of the resistance 3. So conductance is inverse resistance. It's equal to 1/3. This number is 1/3. And it's 1/3 to extremely high precision. Let me just. So I don't know why it disappeared here. I wrote that precision here is of order 10 to the minus 6, or even bigger. So this is very precise measurement. So this never happens, of course, in the real world, that you measure something and you get like 1/3 exactly, and then corrections are very small to this actual measurement. So this is some sort of magic. It's called precise quantization of Hall conductance. And this phenomena is was discovered in the late 70s, early 80s. There's a lot of theoretical work. So, so now you can see why this could be a candidate where kind of similar ideas as CFT, level quantum gravity, may have something to do with this. Not directly, but it's a candidate. So first of all, it's 2D, two-dimensional phenomena. Then actually CFT and holomorphy do play a role, as I will explain a bit later. And it's also strongly interacting system. So like Liouville theory is interacting with quantum field theory. Now, what I will talk about, there are different approaches actually, which are called random geometry or quantum geometry in this quantum Hall effect, that I will not talk about. So there is a approach developed by Zimbauer, Gruber, Sidrakian, and others. It's called random 2D geometry and plateau transition. So they talk about what happens if you go from this plateau to this plateau, plateau transition. So what happens? Like, there are some scaling dimensions there. There are some and the random geometry kind of description. This is something I don't know about, I will not talk about. There is another approach by Haldane called quantum geometry of quantum Hall effect. It's also something different. So I will talk about more like classical description of quantum Hall effect. So we will talk about Laughlin state. And Laughlin state is an explicit wave function which describes electrons which live here. And for example, in this picture, Laughlin state corresponds to this plateau 1/3. All right. So what's the definition of this Laughlin state? So I will start with the original. I will give, I think, 3 definitions. So to make sure that to cover as much as possible of the audience, because different people familiar with different things. So I give myself 3 positive integers, n, d, beta. So these integers have their names. N is a number of particles on complex plane. So I will, of course, consider that we live on a for now, we live on a complex plane. So in principle, this quantum Hall effect happens in the domain where this sample in some sample which is domain of a complex plane. So n is a number of particles that will be labeled by complex coordinates z1 to zn. Number d is called degree, and it's related to how much magnetic field do you have per unit of area. So it's called flux of magnetic field. So the degree, it will be integer for me. And 1 over beta will be that number p over q on the previous transparency. So this will be quantum Hall effect with Hall conductance given by simple fraction, 1 over beta. All right, then the Laughlin state is a polynomial with complex coefficients of these n variables, z1 to zn, which is degree d homogeneous, completely symmetric for even beta, or completely antisymmetric for odd beta, and vanishing on all the diagonals, where zn is equal to zm, 2 order beta. So why such a definition? So first of all, this polynomial, this state is a wave function, which is a holomorphic, as you see. So it's a polynomial in z's, not of z bars. So it's holomorphic because the Hamiltonian, which you will see in a second, prefers to be in the ground states because we are lower temperature. So all the electrons in the ground state, and ground state is holomorphic. It's this condition of antisymmetric is because electrons are fermions, so wave functions are completely antisymmetric. This is for odd. And for even beta, this is a wave function of bosons, which is not in quantum Hall effect, but it's used for other purposes, called atoms or other things. So we could, in quantum Hall effect proper, one considers beta odd, but for beta even, such states also make sense. And why this vanishing on the diagonals? This is because the system is strongly interacting, and to capture this, we require this state, this wave function, to vanish when the electrons are very close. They're close, psi tends to 0 very fast, to order beta. So this captures that they don't like to be close by, so they interact this way. So now this was a general definition for n beta and d. If we take this particular value of number of particles as a function of d and beta, so I have to assume that d, integer number d, is divisible by beta for this to make sense, because number of particles is always an integer. So if it happens that NAD is related like that, then there is a unique Laughlin state. And it's just given by the product Zn minus Zm to the power beta. Nothing else. So it's only unique state which satisfies this definition. So meaning that if you want to increase n by 1, there will be no state. Impossible. So the terminology is that this state is completely filled. So we took all electrons and we cannot add one more. Now, I'm saying state, I mean wave function. So wave function means that it's an element of L2. So in this case, it's L2 of Cn and copies of complex plane for n particles. And L2, then in L2 with this measure where I add this exponential. This exponential involves degree, which is basically magnetic field. This exponential due to magnetic field. And this is just a product of Lebesgue measures. So And in quantum mechanics, wave functions should be normalized. So with respect to this L2 measure, L2 structure, I need this psi to be normalized to have L2 norm 1. And accordingly, I can choose constant C here. So that's one definition. Are there any questions so far? So you may ask, where's the Hamiltonian? I'm talking about quantum mechanics, where is the Hamiltonian? So if you wonder, where's the Hamiltonian? So here's an equivalent definition with the Hamiltonian. That's a little bit less, a little bit more heavy. So I can say that Laughlin state is a polynomial of these n variables, which is a minimizer of this L2 product for the Hamiltonian, which looks like this. So I'm going to explain. So this is like a kinetic term of the Hamiltonian. So d bar is a d by dz bar. So d bar kills holomorphic polynomials. So then it's easy that every psi which is holomorphic, this will be killed automatically because it's. So now d bar dagger is an adjoint with respect to L2 structure. But psi is already killed by d bar. And now what's written here, so this is a mess, but it's very simple to understand. This means I want all partial derivatives of psi to vanish on the diagonal. So I take all partial derivatives of psi to the order beta minus 1. And I require that on the diagonal, so to minimize this guy, I need these partial derivatives to vanish on the diagonals. So for example, if I go back to this state, and I take beta minus 1 derivative of this state with all these z1, z2, etc. But total number beta minus 1 partial derivatives, this will still vanish when zn is equal to zn, because like there will be one zn minus zn factor left. So in fact, it's not completely obvious, but these two definitions are equivalent. So requiring the vanishing on the diagonals and that it vanishes with all its derivatives to the order beta, all partial derivatives to the order beta minus 1, and vanishing all the derivatives to the order beta is the same. So this Hamiltonian is a little bit strange because it's very, very non-local. But it has this property that Laughlin state is an exact eigenstate. I think it's called Haldane Van Hamiltonian. It goes back to 1983, but I might be wrong about the exact name, how it's called. So now there is a third definition, which is also equivalent to these two, but it applies when we replace complex plane by a complex Riemann surface, sigma of a genus G. So now why do such a thing? So in fact, it's very useful often to go from the plane to a compact surface if you are interested in the phenomenon in the bulk. I don't want to deal with the boundary, for example. That was one initial motivation, because boundary phenomenon is always complicated. So let's choose the boundary conditions, or let's put a system on a sphere, on a torus. That's a usual kind of thinking in physics. So it turns out to be a useful idea to consider the Laughlin state on a compact Riemann surface. So for this talk, it's enough to have sphere two-dimensional sphere in mind. So I wrote here genus G, but in fact, genus 0 will be enough for this talk. So now there are no holomorphic polynomials on a compact Riemann surface, except a constant one. So instead, we have to talk about, instead of holomorphic polynomials, we have to talk about positive line bundles. And degree of a polynomial will correspond to degree of a line bundle. And technical condition is that the degree should be greater than 2g minus 1. So now I have, instead of complex plane, I have n copies of Riemann surface. Pn is a projection to nth element in this product, sigma n. And this kind of bundle lambda box, tensor box, is basically saying that Laughlin state is a holomorphic section if you fix any particle, if you look at any particle in that Laughlin state. It's a holomorphic section of this line, of the one and same line bundle L. So in other words, it's saying that it's a homogeneous polynomial of degree D on the plane. I replaced this by this condition that it's a section of this line bundle. And these two conditions are the same, that it's completely symmetric or anti-symmetric for beta even odd. And vanishing on the diagonals is the same because diagonals are local. So you're just saying that locally this holomorphic section vanishes when Zn is equal to Zn. Now, in this setting, completely filled state corresponds to a number of particles is a little bit modified. It's d over beta, and I have to take d divisible by beta, plus 1 minus genus. And there is, you cannot add more particles than that, then there will be no Laughlin state. So this is this is to give us some sort of, this slide is to give some sort of formula for what the Laughlin state, what's the analog of that Zn minus Zm to the power beta, which appeared before. So here I'm trying to explain the holomorphic line bundle. So I have my Riemann surface, sigma g. I look at some local chart. Line bundle means that I have a complex line for each point of the surface. And holomorphic sections means a map from from base to this line, S of z, which is holomorphic locally on this chart. And then I need holomorphic transition functions for the intersections of two charts. And the anti-holomorphic derivative, which I had on the plane, will be replaced by d-bar operator for the line bundle, which acts on from C infinity sections to 0, 1 forms with coefficients in C infinity sections. So for beta odd, the Laughlin state is fermionic. It's completely antisymmetric. So it lives in, it's completely antisymmetric. So it lives in antisymmetric wedge product of the vector spaces of holomorphic sections for each Riemann surface. And I can write this completely filled state as an example. I can write as determinant of this square matrix. So this square matrix is section Sn at a point Zm, and Am vary from 1 to n. So I take the square matrix. It's called Slater determinant. So what does it have to do with Zn minus Zm to the power beta? So on the complex plane, on a compactified sphere, this is basically saying that Zn minus Zm to the power beta product n less than m is actually the Vandermonde determinant. How do I write this? It's it m to the power n minus 1 m from 1 to n to the power beta. Right, so I can, on the plane, I can write this product as a Vandermonde determinant. And on the Riemann surface, instead of these polynomials, z to the power n minus 1, I look at these holomorphic sections. So it's the same analogous result. Instead that, except that here I have to take sections of a line bundle of degree d divided, so the L is degree d, so I need to take line bundle of degree d divided by beta. That's why I take L to the power 1 over beta. Because I take 10 to the power beta. So to have overall degree d, this is how I construct it. So now, since I'm on a Riemann surface, so I will remind you that we can put a metric on the Riemann surface in the conformal class. So you can write a length element as gzz as a single function, gzz bar, dz bar. This is putting the metric in conformal coordinates. And the analog of my, they were on the plane, they were exponentials of Gaussian exponentials. On the Riemann surface, this corresponds to Hermitian metric. So Hermitian metric at each point, it takes the length of a section as a positive real number. And curvature of this Hermitian metric is a magnetic field, as a meaning of magnetic field. And the flux integral, integral of a magnetic field over this compact surface gives this degree d. So now Laughlin state is L2 of Riemann surface product n times with itself, and d mu I replace by volume forms with respect to this metric times this Hermitian metric. So before I had here, I had product of exponential minus d z n squared d2 z. So I basically write the analog of that for on the Riemann surface. Now, since I'm in quantum mechanics, as I said, I have to normalize. So I have to compute L2 norms. So for Laughlin state, I just take absolute value of psi squared. Oops, and I forgot to insert this product of exponentials, which I just, so I'm gonna consider constant d. So degree is equal to magnetic field. You can see the constant magnetic field. All right, so that by 2, for some reason I have 1/2 here. So this, of course, I can write in this form, which is a Coulomb gas. Right? I take this Vandermonde factor Zeta minus m to the exponential. So this is a partition function of 2D Coulomb gas. Right? And on the plane, it's a number. It's a real number which depends on real number b and beta and n. So it's not so interesting as an object. Instead, you may want to consider, so in Coulomb gas, you may want to consider adding here a potential function. So with nice boundary conditions at infinity so that this integral converges. or in this more geometric setting, which I on a Riemann surface, you look at the potential function as the sum of two terms. So one term is function phi. So phi is related to exponential of minus phi is this Hermitian metric. And magnetic field is Laplacian of logarithm of Hermitian metric with a minus. It's Laplacian phi. And this term of order 1 over n, I wrote as log square root of g, so that when I put it here, then square root of g, that goes into volume form here, and I get integration with respect to the volume form on complex plane. So if I choose this metric properly of volume form, I can consider sphere. Right? For example, if square root of g is exponential of real function sigma times round metric on a sphere, I get a sphere with an arbitrary conformal metric parameterized, which parameterizes arbitrary kind of metrics, smooth metrics on sphere. So this is something you're familiar with in Liouville quantum gravity. This
sorry,
conformal class.
may I ask a question?
Yes.
Yes. Sorry, can you say it again? How this Hermitian metric is that is not, so that is arbitrary that you can choose, and why that measure L2 you use this Hermitian metric as the measure? Is that?
So this one I have to use I have to use this Hermitian metric because section this holomorphic section without Hermitian metric, it's not a function on a surface. It transforms when I go from chart to chart. If I take this Hermitian, this section computed with the Hermitian metric, it gives me a real valued function on a surface, which I can integrate, for example.
And how flexible are you in choosing Hermitian metric? Is a large class?
I want to consider the case where minus dd bar log h is strictly positive.
That's the only restriction.
Yes, it's also smooth. So C infinity. So all derivatives are smooth. Now,
or maybe also some integral class.
Yes. So this gives me the condition that the integral of so essentially this is the integral of this guy over the surface is integer.
Okay, thanks.
Here I define B by multiplying by inverse metric, and I integrate with respect to volume form. So this is saying that this integral of this function of dd bar log h over the surface is integer. It's very interesting to consider non-positive case. Then you're going to have a boundary. This will create a boundary. And this will be a boundary effect. But I will not mention that. So there is a generalization of all I'm saying for the case where there is a boundary, which is very interesting, but I'm not going to have time to mention this. All right, so now this is much more interesting object. It depends on this potential of phi and metric. So this is something we want to compute. So the best mathematical result is very recent. So for log z as n goes to infinity. So you could consider large n limit. We have this many electrons on surface, on the domain, on the complex plane. So we send number of electrons to infinity. All the equations will be in this limit. So Leblet-Serfati computed this expansion, which begins with n squared. So there is n squared times the functional, which is called Dirichlet logarithmic energy. Then there is a constant n log n, just independent of the metric. Then there is a constant of n times a constant, which is kind of universal terms independent of the potential. And then there is this term of order n with the coefficient 1 minus beta over 2, which looks like entropy. Mu v log mu v. And mu v is a minimizer of IV. So in fact, they have a more general result for large deviation principle, but for my purposes, I only quote this kind of corollary of the more general theory. And the corrections are small o of n. So in fact, the boundary corrections will come at the order square root of n. But I'm not considering the boundary. Now, the essence what I want to communicate to you is that there is a conjecture for the order 1 term. So there, in the case where there is no boundary, when all the metric and Hermitian metric and Riemann metric are C infinity, the conjecture is that, so we have also the n squared order n terms, which are essentially as in the theorem of Lebesgue-Serfati. And order 1 term is right here. So order 1 term, it comes with this coefficient 1 minus 3 beta over 12. And this is a Liouville function. This is very familiar to most of you, Liouville functional, which is used in Liouville quantum gravity. So here I wrote S1, S2. And of course, this one should be S2 and this one should be S1. And it's a little bit not obvious how to recognize this one as directly as this logarithmic energy, but it's true. So in terms of phi, logarithmic energy becomes this thing, this Gaussian kind of energy. And this S1 will contain also this entropy term, which is right here, because sigma is a logarithm of the metric. And this is just the Liouville function written in a conformal gauge for the metric. Sigma is a conformal exponential of while factor of the metric. Now, they might be a constant independent of this potential function of independent of metric sigma. And the point is that there are these corrections which are smaller than which is order small o of 1, which vanish as n goes to infinity. So this correction term f is a local functional of b and scalar curvature of the metric, meaning that it's a polynomial of b, r, and its derivatives. It's an integral of a polynomial of b and r and its derivatives. And for constant, if we put constant b, as I did already, constant magnetic field, this correction is actually begins with the order 1 over n. And it's simply integral of r squared, integral of curvature squared. So this is a conjecture. This is not proven. This is only, we only have physics kind of derivation of this, of this, and more importantly, of this Liouville term, except for the case beta equal 1, where it's a theorem. So for beta not equal to 1, this is a conjectural result, which is seen by Wigman and collaborators. They use something called loop equations in random matrices. And with Ferrari, we used actually, there exists a Gaussian free filter representation of this Laughlin state. So I will briefly mention this. So in fact, Laughlin state mod squared can be represented as expectation of a string of vertex operators. So these are exponentials of Gaussian free fields. The difference with Liouville quantum gravity is that these exponentials come with imaginary E, they're imaginary. And phi is a Gaussian free field on the sphere. So this is for the sphere. More precisely, so I will speak in terms of action functional. So this Gaussian free field is d phi, has the action d phi d bar phi, and then there is a linear term in phi. So this is in Liouville theory there is a background charge. Here there is also this background charge term, but it's imaginary. It's purely imaginary. In Liouville theory, in pure Liouville theory, this coefficient is real. Here it's purely imaginary. And then I add another linear term, which is multiplied by the magnetic field, and it's also imaginary. Then it can be shown that this expectation value with respect to this exponential action actually gives Laughlin state mod squared. And to compute this remainder term, which is small, which should vanish as n goes to infinity, you kind of have to consider add this exponential interaction to this action. So this is purely on physics level of rigor, that the perturbation theory in this path integral at large n will give terms which vanish as n goes to infinity. So there is a this is conjectural, and it would be nice to kind of understand this path integral as we have understanding of, for example, Liouville quantum gravity, the exponentials of Gaussian free fields in Liouville quantum gravity. But so far it's a conjecture. So what's the meaning? I will remind you what's the meaning of this. So there is a Liouville function of why it's a big deal. So it's so what's the meaning of this Liouville order fun term, meaning the Liouville term? So this is Liouville functional signifies the anomaly of the Zeta determinant. So this is maybe Osgood Philip Sarnak is a good source where this is explained. So they consider the eigenvalues of the Laplacian operator. They define the zeta function for the spectral zeta function for the positive eigenvalues. And determinant, regularized zeta determinant is this exponential of minus first derivative of zeta function at 0. And the anomaly formula is that if we change the metric in the same conformal class, this ratio is exponential of the Liouville function, of the Liouville action. And also the partition function of Gaussian free field is zeta determinant to the power minus 1/2. So this signifies that there is a Gaussian free field somewhere in this wave function. Now, for the case of beta equals 1, which is the integer quantum Hall effect, we're sure that there is this Liouville action at the order 1 in this expansion of the logarithm of partition function. So this is because, so the wave function is, in this case, we just need to take antisymmetric combination of the holomorphic sections. This is Slater determinant. We take the Slater determinant, we take its norm, Hermitian norm with respect to Hermitian metric H, and we integrate it with the volume forms over all particles. And so log Z has the expansion which begins with D squared. So D is a number, it's not a derivative. Right? So D is a degree of a line bundle. So this expansion begins with D squared. So for large d, meaning large number of particles n, because n and d are connected. N is d plus 1 minus genus. So if d genus is fixed, so d goes to infinity, means n goes to infinity also. But this expansion is in terms of d. So there is second term is this number d times another functional. So these functionals actually have names in geometry. The leading one, which we call Dirichlet, it's called Aubin-Yau when we parameterize metric through the Kähler potential. The second term is called Mabuchi, and here is this entropy, this entropy term G log G. And the third one is Liouville. Now it comes with coefficient 1,6 because we put beta equal 1. So there is no beta equal to 1. This is just a number. And this is a Liouville, which is not written in conformal form. It's written as a function of the metric. And corrections are small in 1 of ups. Should write 1 over d. So this can be established by the variational formula. So the variation of this z with respect to phi can be expressed through the Bergman kernel. And BD is a Bergman kernel, which is a sum over all Hermitian norms of the individual sections from 1 to n. So this object has a large d expansion for large degree, which begins with constant d, and there is 1/2 curvature, Ricci scalar curvature of the metric plus small corrections at large d. And this formula can be integrated to give all these functionals. So for beta equals 1, we are sure that there is indeed this Liouville theory, Liouville functional there. Now, so we see the Liouville functional, but why do they think that it's related to this Zeta determinant? Because Liouville Zeta determinant is more complicated object. And we just see the Liouville function for smooth metrics. So in fact, what can be checked is that it's indeed Zeta, this Liouville function comes from the Zeta determinant. Is if you consider the same partition function, but on a singular surface. So I consider this on a cone. So it's a flat cone with a singularity of angle alpha. Or there is another geometry called spindle. It's a kind of sphere with two cones, which are antipodes. And there is a constant scalar, there is a metric of constant scalar curvature, which you can put everywhere except the singular points. And you can compute the partition function for large n, and you see that indeed there is a Zeta determinant of singular, of the Laplacian on a singular metric in the power minus 1/2. So there is a partition function of the Liouville of the Laughlin state at beta equals 1 gives indeed this Zeta determinant. So this this is sort of motivation of the why Wigman and Zabrodin kind of suggested this problem. So how can we represent this partition function as a path integral? So like in Liouville theory, we integrate over all metrics on a surface with some weight given by Liouville theory. So they asked back in 2006, how could you represent kind of this calculation of normalization of Laughlin state as a kind of sum over all, in a way, over all metrics? Because so they thought about empirical measure. So they looked at empirical measure, which is sum over deltas, Dirac deltas for each particle. And this is kind of, so this rho is sort of like a very singular metric on the surface, which is supported only at the points where the particles are. So they thought that this as some sort of like integral over the singular matrix on the surface. And so they actually more recently they decided that beta variable, so to define something like this, beta variable is this phi, which is sum of logarithmic potentials. And Laplacian phi, if you remove n, this will give this rho. Maybe I have to add something here. Maybe and that's squared or something. Anyway, so this potential, or maybe no, because we are on this because we're on a sphere. It's not necessary. So they proposed something like this. So the integral over this phi, which they thought about as think about as Gaussian free field, and this action. So it indeed contains GFF action with it now with real coefficients, but then they have to add some sort of corrections, which are functions of rho, meaning that they're functions of phi. So this is this one is this entropy, and this one is kind of Liouville functional when rho is thought of as a metric. So this if sort of you add all these three terms and you think of this action or this path integral as kind of perturbatively, you can reproduce the results in for the density of states, for example, in Liouville, in a Laughlin state. But this kind of looks very complicated. So the Gaussian free field is actually not. It's not really the Weil factor of the metric exponential. When you put metric in a conformal form, in Polyakov theory, the Weil factor is quantized as Gaussian free field. Here it's more like Laplacian of phi is a metric. And that's why they need kind of corrections here. Now this, there are related mathematical results for the Geneva ensemble. So one you probably know about is by Ryder Virak and Hedenmalm and others, that if you take Geneva ensemble, so this is for beta equals 1, then so for a test function, this object this is a random variable which is has mean 0 and variance sigma. This is like a Gaussian free field, right? And this is exactly this phi integrated against rho. And more recently, there is this conjecture by Wong, which I copied this from their paper. So this is expectation in Geneva ensemble of the characteristic polynomial. So this is like an exponential of phi with the coefficient gamma. So if phi is thought of Gaussian free field, this is like exponential of exponential, a product of exponential of Gaussian free fields. So this is sort of related to this previous approach of Wigman. Now, what's a little bit, of course, what's a problem in relating this to Gaussian free field or something like Liouville theory or conformal field theory is that the Laughlin state contains magnetic field, and magnetic field is a length parameter. So this object is not conformal. So everything you will get with free field or Liouville quantum gravity will contain no dimensional parameters. It's a conformal theory. And here, as long as you have n, you have degree related to n, and this makes all these objects non-conformal. So if you want to relate a Laughlin state to CFT or to a level quantum gravity, you have to get rid of n somehow. And in all these objects, like there is a part which contains n, and then there is a part which looks conformal. So I'm almost done. So I have to finish already, right? Do I have 2-3 minutes or?
Yeah, sure. Another 2 or 3 minutes.
Yeah, I'm almost at the end. So it appears that this there is a kind of conformal field theory structures in this calculation of this partition function for Laughlin state, but it appears when n goes to infinity, and there are always these large n terms, n squared or the squared or the n, which kind of hide this conformal structure. So how to see this conformal structure, which must be a theory of random metric, because like this configuration of points defines a sort of metric on the surface. One idea due to Riemann is to consider, and collaborators, is to consider the regime where we're on a singular surfaces. And when surfaces are singular, this gravity, this metric part, becomes dominant. And they see this emergent conformal symmetry when you have several kind of singularities on the surface in this paper. Well, you may try to cook up another object where you kind of make this large n term disappear, and you end up with only order 1 term, so that you get rid of this large deviation kind of part of the problem. So this is in my last slide or two. There is an attempt. So I consider, so again, as before, a compact Riemann surface, a degree k line bundle. Same thing, curvature. I consider constant magnetic field, meaning the curvature of Hermitian metric is proportional to the Riemannian metric with the coefficient k. And now I choose this basis of sections to be orthonormal. So I didn't do this before. Now I require this basis to be orthonormal. And I fix beta must be greater than 1. It doesn't work for beta equal 1. And I consider the following measure on configurations of endpoints on the surface. You take this determinant, Slater determinant, computed in Hermitian metric, and take it to the power 2 beta. And this is product of following forms. Now, the total mass only depends on G, on the metric G. It's kind of background independent. I didn't use any background matrix, I just used G only. And the Weil anomaly formula now contains only Liouville term with coefficient beta minus 1. So this object doesn't have this n squared and n terms. By choosing orthonormal basis, I got rid of them. So what I get here looks like a lot like a property of Liouville quantum gravity, because it's background independent, and there is a Weil anomaly. It's almost like defining properties. So this would correspond to central charge beta minus 1. That's it. So that's just that's the end. So this I didn't This is just a suggestion.